All right, so moving on to the last couple problems. We've got 16, a boy, runs past his sister at a constant rate of 3 meters per second. 0.4 seconds after he passes, she begins running after him, accelerating at a rate of 1.5 meters per second squared. When does she catch him, and how far has she moved the moment she catches him? So to visualize what's going on, you have the girl just standing there. Say, you're both in the road. She's just standing there, and she's watching her brother run past her. As soon as he passes her, 0.4 seconds later, she bolts off to try and catch him. So that's what's happening. So the question is, when does she catch him, and how far has she moved when she catches him? What do we need to do to be able to figure those things out? So we need to find a time. When does she catch him? When is code word for how long, what time did it take to catch? And then we need to figure out where is the girl's final position, because that will tell us how far has she moved once she catches him. So just labeling all of our knowns and unknowns to be able to solve for the time that it takes to catch him. What do we know about their final positions? To be able to catch somebody means that you and them, you and they, you and them are in the same spot, which means you and the other person have the same final position. So that's the key here. You both have the same final position. So what you can do is you can set those two final positions equal to each other and go off of that. You don't have to know what that final position is. You just know that those two are equal, because what you have to do is you have to separate the motion out. We can't combine their motion together. So we have to treat the boy separately. This is just 1D motion for the boy. And then we have to treat the girl separately. This is 1D motion for the girl. We know how to do 1D motion. This is just motion in the X direction. The only difference now is we've added a little more difficulty to this problem where we're comparing these two motions together. So this is just a 1D problem, and this is just a 1D problem. And then what we're doing is we're linking them together. So you solve for the final position for the boy, you solve for the final position for the girl, and you set them equal. So that's what we're doing down here on this first step. You're writing an expression in terms of time, since that's what we're looking for the boy, and then for the girl. We know what the initial positions are. We know what the acceleration is. And we know what the initial velocity is. So we can solve for the final position. There's one unknown, which is time, which is what we need. So we can solve. Because remember, we are setting these two equal to each other. The final position of the boy and the final position of the girl. That's why I have that being the key. That's probably the hard part to pick up on. What does it mean when the girl catches the boy? Well, that means they're at the same final position. Setting those two equations equal to each other, they both are in terms of time. One of those t's cancel out, and you can solve for time. You find that the time is equal to 8 seconds. It takes the girl 8 seconds to catch the boy. Now, how do we find out how far she's gone? Well, we just use the same equation that we did in part 1. We use the equation for the girl to find the final position, and we substitute in the time that we just found. So it's a little different. than what we're used to, where we're reusing the same equation that we did again. But we're just making use of the fact that we solved for time now. So we can actually use that to solve for the final position of the girl. We find that she is 48 meters away from where she started. So moving on to the last problem, we have you get a new bow and arrow set for your birthday. You shoot an arrow from 1.1 meters above the ground with an initial speed of 24 meters per second and an angle of 30 degrees above the horizontal. 1.5 seconds later, it narrowly misses the peak of your house roof when it's on the way down. The arrow lands on the ground. So that's actually a key piece of information. Determine the final velocity, magnitude, and direction. Determine the horizontal range of the arrow. So this is a pretty typical problem for projectile motion, where you are starting at some height and the final position is not at the same level. So this is going to be a pretty typical problem for projectile motion that you'll see. As with everything, you always want to draw your initial velocity in terms of its components. Remember, with projectile motion, you deal with it in terms of motion in the y direction plus the motion in the x direction. That figure from the note packet that splits up the motion into its x and y components, because that is how you treat projectile motion. Then in the end, you just combine what you find to get the overall, in this case, and in most cases, the overall velocity. So once you break down into components, one thing that I've seen over the course of the week is choosing the correct angle. So depending on what you're given, in this case, it's above the horizontal, you sweep your angle through the horizontal. So we've got a horizontal here. You sweep your angle through up this way, whatever angle you're given. And so that is your angle theta. And in this case, that's 30 degrees. So make sure you're keeping an eye on how you're drawing these triangles, because it matters. It's going to dictate which trig function that you use, sine or cosine. And ultimately, it ends up affecting the results. So sometimes with velocity, it'll cancel out. But if you're solving for time or distance, then it won't. And that's when it becomes an issue. Other than that, you just set up the problem like we normally do in free fall. Whether it's on its way up or it's on its way down, the acceleration in the y direction is constant, 9.8 meters per second squared, pointing downwards. Acceleration in the x direction is 0 for projectile motion always. Knowing all of those things, we can now move on to solving for the final velocity of the arrow. We know the initial velocity in the y direction. We know the acceleration in the y direction, as we just discussed, and we know the change in position from the start to the finish in the y direction. So we can ultimately solve for the y direction's final velocity. We find it's negative 12.9 meters per second. So that means our y component of the final velocity needs to be pointing downwards when we draw the components to combine them into the final velocity. How do we get the final velocity in the x direction? Well, acceleration is 0 in the x direction, so as soon as you solve for the component in the initial velocity in the x direction, then you know what the final velocity x component is. That's going to be pointing towards the right, since we are moving in the positive x direction. So that's how you draw these triangles. You know which direction your vector should be pointing. The x direction should be pointing to the right. We just talked about we have a negative y final velocity, so it needs to be pointing downwards. And that's how you construct these triangles so that you don't mess up what the angle is. You can't just draw a triangle however orientation that you want. There's actual reason and procedure for drawing these triangles. You construct them based off of the signs that you have for your values. So then you just draw your resultant vector. You start at the tail of the x vector and you finish at the head of the y vector. Remember, your resultant vector gets you to your final spot. So the components get you to the final spot, but your resultant vector takes you directly to that final spot. We can use Pythagorean theorem to solve for the final velocity. And then we can use the angle, we can define an angle to determine what the direction is. So you can use inverse tangent, opposite over adjacent, Vy over Vx, to find the angle, and that is measured from the horizontal. This is the angle 31.8 below the horizontal. This is key. You need to specify what this angle is being measured from. So it is sweeping through from the horizontal. So it's going this way. So that means it's below the 31.8 degrees below the horizontal. Again, this is key. You need to specify that. Then we're asked for the range. So for range, we know that the acceleration in the x direction is 0. So we just have position as a function of time and velocity in the x direction to solve for range. We're missing time, so we need a way to solve for the time that the arrow is in the air. We use the y direction for that, since that's what dictates time. We know the initial and final velocities because we just solved for the final velocity. We know the acceleration, so we can solve for time. Once we have the time, then we can just substitute that in to our position as a function of time equation. We know what the initial velocity is because we solved for that component at the start. And we find that the range is 52.8 meters. And so this is a pretty typical problem for projectile motion. You start at a height. I know I'm repeating myself, but it's a pretty common problem where you start at some height and you finish at a different height. You're given some piece of information about the velocity and maybe some distance or time, and then you're asked a series of questions to solve for based off of that information. So this problem and this last problem are ones that you should study because these are pretty representative of dealing with here one-dimensional motion. So this is module 1 and 2, and then here and this is projectile motion, which is module 3. So these two problems really encompass what we've done so far in this course. So if you've had trouble with these two problems, then I would suggest figuring out where was your mistake. Think about it. Was it just a silly error? Was it something with your deeper understanding that you were missing? Go back into the notes, go back into your practice exam, practice problems in the notes or the homework. And if you're still having trouble with it, you need to contact me and we need to clear that up because these are problems that we've dealt with before. They're just kind of represented in a new way, but the underlying physics is all the same. So if you have trouble with it, that means that maybe the concepts aren't necessarily clicking and we just need to work through that and get you on the right track. So with that, good luck on your studying. Use this as a guide and best of luck on